And welcome. Uh, you must have seen this picture before because this figure was a part of IIT problem, previous year's IIT problem. I don't exactly remember the year, but this problem is a bit modified. So you need to read the statement of the problem first, and statement being a thin electrically insulated wire bent at right angles at both ends has a soap bubble. In fact, it has two soap bubbles of radius smaller and capital R. How much electric charge should be given to one of the bubbles? Which one? I don't know yet. So that the size of the other bubble does not change after a tap in the middle of the wire is opened. So what is happening now when the tap is closed? And I can simply write here that the pressure inside this smaller bubble is being outside pressure plus 4 sigma by r. Of course, sigma is the coefficient of surface tension. Without it, we cannot move a bit. So we have to consider it, and pressure inside this larger bubble is outside pressure plus 4 sigma by capital R. And you can see here that small r is less than capital R. That means PR is greater than PR. And if we were to open the tap, the smaller bubble is simply going to deflate completely, and larger one would expand. And it is our job to prevent this, to make this larger bubble into the size, and we also need to save the smaller bubble from deflating. That means we need to put some charge on this smaller bubble to increase its radius. It can be positive or negative, any charge, because charges are going to repel each other, so that its radius will increase. And when its will increase, the pressure inside will decrease, and we have to keep it at pressure inside this larger bubble so that its size remains intact. It should not change. So we need to make some changes to the smaller bubble, put some charge over its surface and increase its radius. But how much? We don't know yet. So I'm going to use the Boyle's law, because the process will be fast and temperature will remain constant, I guess. So I can write the Boyle's law for a smaller bubble, like its inside pressure is PR now, and its volume is 4 by 3 pi r cube. And this future pressure, we are going to make it PR equal to the inside pressure of the larger bubble, and its volume as 4 by 3 pi x cube. X is its new radius. We don't know what is it, but we can find it as x will become third root of PR by PR from this equation, and it can be expanded like P naught plus 4 sigma by small r plus P naught plus 4 sigma by capital R multiplied by R. R should be here too. Yeah. And to make its radius equal to x, increase its radius from a small r to x, how much charge we need to make it happen. That means we need to determine how much charge q will cause the radius of the bubble of radius small r to change to x, and so that it will there will be an outside electric pressure created over the smaller bubble due to charges with outside pressure. It's simply PQ, and inside pressure is PR, and its radius is X. So that I can write here as PR minus electrical pressure created, inside pressure minus outside pressure, should be equal to 4 sigma by X. So this is one of the equations we are going to use in picture. And to solve this problem, I'm going to consider this a smaller bubble as a sphere of radius x and charge q, and I can write its capacitance as a capacitor. We know that capacitance of a spherical capacitor can be written as 4 pi epsilon naught multiplied by its radius. And if I can put 1 by 4 pi epsilon naught simply as k, so this will become x upon k. So it is its capacitance, and its electrostatic energy or potential energy is q square by 2c now. So that I can write it will become k by 2 q square by x in terms of k. And now I have to find out this PQ. That means I need to relate PQ and Q, and to do so I'm going to find out du, and that will be equal to minus k square by 2 kq square by 2 1 by x square dx. And this du can also be written in terms of work done, force multiplied by this small displacement x, and the force being pressure PQ outside multiplied by 4 pi x square, the surface area, and the displacement dx. So that I can find here PQ will be equal to kq square by 8 pi x raised to 4. And now I can use this relation. That means PR minus PQ equals 4 sigma by x. This is the relation. And the PR is simply 4 sigma by capital R. We can write it because this is equal to, so, and PQ will become kq square by 8 pi x raised to 4, and that will be equal to 4 sigma by x. And you can calculate this relation to find the value of q. And what I got finally, that q square will be equal to 32 pi sigma divided by k x cube minus x raised to 4 by r, and that is my answer. I don't want to put a square root because the expression itself is scary, and I don't want to put a square root to look it more scary. So thank you very much for watching.